And today, we are diving into the world of atomic orbitals and, yeah, their advanced applications. It's going to be an interesting one.
Absolutely. I mean, it's back to basics in a way, right? We're talking about the building blocks of matter, but then we're going to zoom out and see how these, I guess, kind of abstract concepts actually underpin all sorts of cutting-edge technology. You wouldn't believe it.
Right. We've got our paste and text, as always, a great set of sources. So our mission, if you will, is to kind of extract the key insights from this material, but go way beyond the basic chemistry that, maybe we all kind of vaguely remember from school,
Yeah.
and to see how this understanding of atomic orbitals, even the manipulation of them, is driving innovation in some crazy fields. I mean, we're talking medicine, material science, electronics, and of course, the ever-tantalizing quantum computing. Buckle up, folks.
I think it's worth starting with quantum mechanics, right? Because that's where the whole concept of atomic orbitals really comes from.
Right, right. It all starts with that, what is it, the Schrödinger
Yeah.
equation.
Yeah, the Schrödinger equation. Now, don't worry, we won't go into the nitty-gritty math here, but basically what the Schrödinger equation does is it gives us these things called wave functions, right? Which describe the probability of finding an electron in a certain region around the atom. It's not like, those old models where you had electrons whizzing around the nucleus like planets around the sun.
Right, those little solar system models that we all grew up with.
Exactly. Instead, what we have are these fuzzy clouds of probability.
So these probability clouds are what we call the orbitals then.
Exactly. Each orbital is characterized by a set of 4 quantum numbers: principal, angular momentum, magnetic, and spin.
Oh yeah, the quantum numbers. I remember those. Sort of. Okay, so the principal quantum number, that's the one that tells you the main energy level, right? Like how far the electron is from the nucleus.
You got it. The higher the principal quantum number, the further away the electron is from the nucleus, and the higher its energy.
Okay, okay. And then there's the shape of the orbital.
Yeah.
And that's where you get into those SPD and F orbitals.
You're on a roll. The angular momentum quantum number determines the shape. So S orbitals are spherical, nice and simple. P orbitals have that dumbbell shape, like 2 lobes on either side of the nucleus. And then the D and F orbitals, well, those get a little more complicated, shall we say, with more lobes and intricate shapes.
Right, like those crazy three-dimensional cloverleaf shapes and things.
Exactly. And the thing is, these shapes, along with the orientation of the orbitals in space, which is defined by the magnetic quantum number, they have huge implications for how atoms interact with each other, how they bond together to form molecules.
So it's not just about where the electron is likely to be, but also about the shape of that probability cloud, how it's oriented in space, and even the spin of the electron. And all of this determines how atoms come together to make molecules.
You've got it. The way these probability clouds overlap and how their shapes and orientations align, well, that's what determines the strength and direction of chemical bonds, and ultimately the entire 3-dimensional shape of a molecule. And it also affects properties like electronegativity.
Right, electronegativity. That's how strongly an atom attracts electrons in a bond. And that's super important for understanding all sorts of chemical reactions and properties, right?
Absolutely. And when we talk about how these orbitals come together to form bonds, we need to move from thinking about individual atomic orbitals to molecular orbitals. This is where molecular orbital theory comes in.
Okay, molecular orbital theory. I remember that term from chemistry class, but honestly, I can't say I really understood it back then.
Well, it can be a bit tricky to wrap your head around. Basically, molecular orbital theory says that when atoms come together to form a molecule, their atomic orbitals don't just stay separate. They mix and combine to create a new set of molecular orbitals that spread over the entire molecule.
So instead of having individual orbitals on each atom, you get these sort of like shared orbitals that span the whole molecule.
Precisely. And this is really important for understanding molecules where electrons aren't confined to a single bond between 2 atoms, like in conjugated systems.
Conjugated systems. Those are the molecules with alternating double and single bonds, right? Like benzene, the classic example.
You got it. In benzene, for example, the electrons in the double bonds, they're not localized between 2 specific carbon atoms. They're delocalized. They're spread out over the entire ring of carbon atoms.
And that's why benzene is so stable and has those unique chemical properties, right? Because of this electron delocalization.
Exactly. And molecular orbital theory provides a really elegant way to explain and predict this delocalization. And this delocalization also has a huge impact on a molecule's optical properties, how it interacts with light. So why certain organic molecules absorb specific colors, for example.
Okay, so molecular orbital theory is pretty powerful stuff. And it helps us understand not just the structure of molecules, but also their properties and reactivity.
Right. And it gets even more interesting when we talk about transition metals and their d
Ah,
orbitals.
yes, the transition metals. They're kind of like the rock stars of the periodic table with all their colorful compounds and catalytic abilities.
That's a good way to put it. The d orbitals in transition metals are where a lot of the action happens.
Right, and the text mentioned d orbital splitting. What's going on there?
So imagine you have a transition metal ion, like iron or copper, surrounded by other atoms or molecules. These are called ligands. And the presence of these ligands actually causes the d orbitals, which were initially all at the same energy level, to split into different energy levels.
Okay, so the ligands kind of mess with the energy levels of the d orbitals.
Exactly. They create this energy gap between different d orbitals. And
Mhm.
the size of this energy gap often corresponds to the energy of visible light.
Ah, so that's why transition metal compounds are often so colorful.
Precisely. When white light hits a transition metal complex, it can absorb certain wavelengths that correspond to the energy needed to promote an electron from a lower d orbital to a higher one. The wavelengths that aren't absorbed are what we see as the color of the compound.
So the stunning blues and greens we see in gemstones, for example, that's all down to orbital splitting.
Exactly. And this principle, which is explained by ligand field theory, is also incredibly important in bioinorganic chemistry and industrial catalysis.
Okay, let's talk about those. Bioinorganic chemistry, that's the study of metals in biological systems, right?
Exactly. Transition metals, with their unique orbitals, play crucial roles in many biological processes. Like, take hemoglobin, for example. The iron atom at the center of hemoglobin uses its d orbitals to bind to oxygen and transport it throughout the body.
Wow, so the very breath we take depends on the behavior of d orbitals.
In a way, yes. And in industrial catalysis, the d orbitals of transition metals are essential for speeding up chemical reactions. They provide a kind of staging ground where reactants can come together and interact.
Right. And a better understanding of how these d orbitals work can help us design more efficient catalysts for all sorts of important processes, from producing fuels and plastics to reducing pollution.
Absolutely. Now, let's shift gears a bit and talk about how atomic orbitals influence what we see in spectroscopy.
Spectroscopy. That's the study of how light interacts with matter, right? Like using light to identify different substances or to study their structure.
Exactly. And the key principle here is that when a molecule absorbs light, it can promote an electron from a lower energy orbital to a higher energy orbital. And when that excited electron drops back down to a lower energy level, it can emit light.
Right, so the absorption and emission of light are directly related to the energy levels of the electron orbitals in a molecule.
Exactly. And by analyzing the specific wavelengths of light that are absorbed or emitted, we can get a detailed picture of the electronic structure of a molecule, which is, of course, determined by its atomic orbitals.
So spectroscopy is like a powerful tool for peeking into the world of atomic and molecular orbitals.
You could say that.
Yeah.
And it has all sorts of applications, from identifying unknown substances to studying the composition of stars and planets.
Wow, so from the tiniest molecules to the vast expanse of space, it all comes back to these fundamental principles of atomic orbitals. Pretty amazing, right?
It really is. Now, the text also delved into a couple of specific spectroscopic techniques: X-ray absorption spectroscopy, or XAS, and electron paramagnetic resonance, or EPR.
Okay, XAS and EPR, those sound pretty high-tech. What do they tell us about atomic orbitals?
So XAS is all about looking at how a material absorbs X-rays. And by analyzing the fine details of the absorption spectrum, we can learn a lot about the oxidation state of an atom, its electronic structure, and the arrangement of the atoms around it. All of this information is intimately linked to the core and valence atomic orbitals of that particular atom.
An EPR.
EPR is a technique that's sensitive to unpaired electrons, and those are often found in the d or f orbitals of transition metal ions. And what EPR does is it allows us to probe the electronic and magnetic environment of those unpaired electrons, giving us insights into things like the structure of metal complexes and the mechanisms of catalytic reactions. Again, it all boils down in understanding how electrons behave within their specific atomic orbitals.
Okay, now let's zoom in even further and talk about nanotechnology.
Oh yeah, nanotechnology, the world of the incredibly small.
And apparently, atomic orbitals are playing a big role in this field too, especially when we talk about quantum dots.
Quantum dots, those are really fascinating. They're tiny crystals of semiconductor material, just a few nanometers in size.
Nanometers, that's like a billionth of a meter. here, right?
Exactly. So we're talking about incredibly small structures here. And what's really cool is that because these quantum dots are so small, the electrons inside them are confined, they can't move around freely. And this confinement has a really interesting effect on their energy levels.
So it's like trapping electrons in a tiny box.
Kind of, yeah. And this confinement quantizes the energy levels of the electrons, meaning they can only occupy very specific, discrete energy levels.
Okay, so instead of having a continuous range of energies, like they would in a larger piece of material, the electrons in a quantum dot can only have very specific energies.
Precisely. And we can control these energy levels by changing the size and shape of the quantum dot.
So by tuning the size and shape of the quantum dot, we can basically control the electronic properties of the material.
Exactly. And that's why quantum dots are so interesting for applications like LEDs, solar cells, and even biological imaging, because you can tune them to emit or absorb light at very specific wavelengths.
Right. I remember reading that quantum dots are being used to create these super vibrant displays with really pure colors.
Yes, exactly. Because you can control the wavelengths of light emitted very precisely. And they're also being used in solar cells to capture a wider range of wavelengths from sunlight and to improve efficiency.
Amazing. And the text also mentions something about manipulating orbital interactions at the nanoscale to create new types of electronic devices.
That's another really exciting area of research. Scientists are learning how to carefully arrange atoms and molecules at the nanoscale so that their orbitals interact in specific ways. And by doing so, they can create materials with entirely new electronic and optical properties.
So it's like building materials from the bottom up, atom by atom, orbital by orbital.
Exactly. It's all about engineering materials at the most fundamental level. And that opens up a whole world of possibilities for creating new technologies.
Okay, now let's talk about something even more mind-boggling. Magnetism and superconductivity.
Ah, yes. Those macroscopic quantum phenomena that seem almost magical.
Right, and the text pointed out that these phenomena are actually linked to the behavior of electrons in their atomic orbitals. But how? I mean, how can something as tiny as an electron orbital influence something as big as a magnet?
Well, it all comes down to the fact that electrons have this intrinsic property called spin. And spin is kind of like a tiny magnetic moment. So each electron acts like a little magnet.
So each electron is like a tiny bar magnet with a north and south pole.
You can think of it that way, yes. And in some materials, like iron, these electron spins can align in the same direction, creating a macroscopic magnetic field.
Ah, so that's how we get permanent magnets. All those tiny electron spins pointing in the same direction.
Exactly. And the arrangement of the atomic orbitals in the material plays a big role in determining how those spins align.
Okay, that makes sense. What about superconductivity? How do orbitals come into play there?
So superconductivity is this really amazing phenomenon where a material conducts electricity with zero resistance. And it happens because electrons can pair up to form these things called Cooper pairs.
Cooper pairs, I've heard of those. But how do they actually form?
Well, it's a bit complicated, but basically the electrons in a superconductor can interact with the vibrations of the crystal lattice, and that can lead to an attractive force between them. And when they pair up, these Cooper pairs can move through the material without bumping into anything, without any resistance.
And these Cooper pairs, their formation is related to the behavior of electrons in their atomic orbitals.
Right. The specific interactions between the electrons that lead to the formation of Cooper pairs are governed by the properties of their atomic orbitals.
Okay, that's pretty cool. And I remember the text mentioned high-temperature superconductors like the cuprates. Those are still a bit of a mystery, right?
Yes, high-temperature superconductivity is still not fully understood. But we know that it involves some really complex interactions between the electrons and the crystal lattice. And researchers are trying to figure out exactly how those interactions work and how we can design new materials that can superconduct at even higher temperatures.
Right, because if we could figure out high-temperature superconductivity, that would be a game changer for all sorts of technologies, from power transmission to electronics.
Absolutely. It would revolutionize so many things. Now, let's talk about another really important aspect of all this. Computational chemistry.
Computational chemistry. That's basically using computers to simulate and study molecules and materials, right?
Exactly. And it's an incredibly powerful tool for understanding and designing new molecules and materials. Because instead of having to do experiments in the lab, we can use computers to model the behavior of molecules and materials based on the principles of quantum mechanics.
So we can basically build virtual molecules on a computer and see how they behave.
Right, and one of the key methods in computational chemistry is density functional theory, or DFT. And DFT is all about calculating the electronic structure of molecules based on the behavior of electrons in their atomic orbitals.
So it's like building a virtual model of a molecule, atom by atom, orbital by orbital, and then seeing how those orbitals interact with each other.
Exactly. And DFT allows us to predict things like the shape of a molecule, its energy, its reactivity, and its spectroscopic properties. And it's incredibly useful in all sorts of fields, from drug discovery to materials science.
Okay, and the text mentioned some more advanced methods too, like post-Hartree-Fock methods. Those are even more accurate.
Right. DFT is a really powerful method, but it's still an approximation. Post-Hartree-Fock methods, like coupled cluster theory, they go even further and try to account for the very complex interactions between electrons, something called electron correlation.
Electron correlation, what's that?
So basically, electrons don't just move independently of each other. They're constantly repelling each other because they all have the same negative charge. And this interaction between electrons, it can have a significant impact on the energy and behavior of a molecule.
So these post-Hartree-Fock methods are like taking those electron interactions into account.
Exactly. And by doing so, they can achieve even higher accuracy in their predictions, which is really important for understanding very subtle effects or for studying molecules that are very difficult to study experimentally.
Okay, that's pretty amazing. So we got all these incredible tools, both experimental and computational, for studying and manipulating matter at the level of atomic orbitals. And that's leading to all sorts of breakthroughs in fields like materials, science, medicine, and technology.
Absolutely. But it's important to remember that our understanding of atomic orbitals is still evolving. There are still many mysteries to unravel.
Like what?
Well, for example, the text mentioned quantum electrodynamics, or QED, and relativistic effects. And those are really pushing the boundaries of our understanding of how electrons behave.
Okay, QED and relativistic effects. Those sound pretty intense. What are they all about?
So QED is this really fundamental theory that describes the interaction of light and matter at the quantum level. And it turns out that this interaction can actually have very subtle effects on the energies of electron orbitals.
So even in a single atom, the electron orbitals aren't perfectly static. They're being influenced by the quantum vacuum, the sea of virtual particles that constantly pop in and out of existence.
Exactly. It's a really mind-bending concept. And then relativistic effects, those come into play when we're dealing with heavy atoms like gold or uranium.
Heavy atoms, like the ones at the bottom of the periodic table.
Right. And because these atoms have so many protons in their nuclei, the electrons near the nucleus are moving really fast, like a significant fraction of the speed of light.
Wow, that's fast.
It is. And when you have things moving that fast, you need to take Einstein's theory of relativity into account.
Okay, so how does relativity affect the electron orbitals?
Well, one of the main effects is called relativistic contraction. And that means that the s and p orbitals, the ones closest to the nucleus, they actually shrink. They get pulled in closer to the nucleus.
So those inner orbitals get squeezed.
Exactly, and that can have a ripple effect on the outer d and f orbitals, making them more diffuse, meaning they spread out further from the nucleus. And then there's spin-orbit coupling.
Spin-orbit coupling. We talked about that earlier.
Right. But in heavy atoms, this coupling becomes much stronger because of the relativistic effects. And that can have a big impact on the electronic and magnetic properties of the element.
Okay, so it's like relativity adds this whole other layer of complexity to the world of atomic orbitals. And we need to understand these relativistic effects if we want to fully grasp the chemistry of the heavy elements.
Precisely. Now, let's go back to molecular orbital delocalization for a moment, because it plays a huge role in understanding the properties of many advanced materials like graphene and organic semiconductors.
Right, graphene. That's the wonder material that everyone's talking about.
It is a remarkable material, a single layer of carbon atoms arranged in a honeycomb lattice. And what makes it so special is that the electrons in those carbon bonds, they're not localized. They're delocalized, they're spread out over the entire sheet of graphene.
So it's like that conjugated system we talked about with benzene, but on a much larger scale.
Exactly. And this extensive delocalization gives graphene some really amazing properties. Like, it's incredibly strong, it's an excellent conductor of heat and electricity, and it's transparent.
Wow, it's like the ultimate material.
It has a lot of potential, that's for sure. And the same principle of delocalization is at work in organic semiconductors, which are being used in things like OLED displays and organic solar
Right,
cells.
organic electronics. That's a really exciting area.
It is, and it's all about designing molecules with specific delocalized pi systems that can conduct electricity or emit light efficiently.
Okay, now let's talk about excited state dynamics. This sounds pretty intense.
So excited state dynamics is all about what happens when a molecule absorbs energy, like a photon of light.
Right, so the molecule gets promoted to a higher energy state.
Exactly. And then all sorts of interesting things can happen as the molecule tries to relax back down to its ground state.
Like what?
Well, the molecule can emit light, it can undergo internal conversion, it can transfer energy to other molecules, or it can even undergo chemical reactions.
So it's a really dynamic situation.
It is, and the pathways that the molecule takes as it relaxes are determined by the properties of its excited states, which are, of course, influenced by the atomic and molecular orbitals.
Right, those orbitals again. They're everywhere.
They are, and understanding excited state dynamics is crucial for all sorts of applications, from designing more efficient solar cells to developing new types of lasers and light-emitting devices.
Okay, now let's talk about something that seems straight out of science fiction. Quantum computing.
Quantum computing, that's the holy grail of computing, right? The idea of harnessing the strangeness of quantum mechanics to perform calculations that are impossible for classical computers.
Right, and apparently atomic orbitals are at the heart of it all.
They are, because quantum computers rely on these things called qubits, which are like the quantum versions of bits.
Qubits, I've heard that term. But what are they exactly?
So a classical bit can be either 0 or 1, but a qubit can be in a superposition of states. It can be both 0 and 1 at the same time.
What? How is that even possible?
Well, it's a consequence of quantum mechanics, and one way to create a qubit is to use the spin of an electron.
The spin of an electron, that tiny magnetic moment we talked about earlier.
Exactly. And the spin of an electron can be either up or down. And we can use these spin states to represent 0 and 1.
Okay, so we're using the spin of an electron, which is influenced by its atomic orbital, to store information in a quantum computer.
You got it. And there are all sorts of other ways to create qubits using the properties of atoms and molecules.
Wow, this is really blowing my mind.
It's definitely a mind-bending field, but it has the potential to revolutionize everything from drug discovery to material science to artificial intelligence.
Okay, one last topic, spintronics.
Spintronics, that's another really hot area of research. It's all about using the spin of the electron to control and manipulate information.
Right, so instead of just using the electron's charge, like we do in conventional electronics, we're also using its spin.
Exactly. And it turns out that we can use spin to store and process information much more efficiently than we can with charge.
And how do we control the spin of an electron?
Well, one way is to use magnetic fields, but we can also use something called spin-orbit coupling.
Spin-orbit coupling, that sounds familiar.
Right, we talked about it earlier in the context of relativistic effects. And it turns out that spin-orbit coupling can be used to convert between spin and charge currents, which is really important for spintronic devices.
Okay, so spintronics is all about controlling the spin of electrons to create new types of electronic devices. And it's all based on the principles of quantum mechanics and relativity. This whole deep dive has been a wild ride.
It has been quite a journey, but I think it's clear that atomic orbitals are far more than just abstract theoretical concepts. They're the fundamental building blocks of matter, and they're at the heart of some of the most exciting and transformative technologies being developed today.
So for our listeners out there, hopefully you've gotten a deeper appreciation for the power and beauty of these tiny, invisible entities that shape the world around us. From the smallest molecules to the vast expanse of space, from the medicines we take to the computers we use, it all comes back to those fundamental principles of atomic orbitals.
And the most exciting thing is that we're still just scratching the surface of what we can do with them. Who knows what incredible discoveries and inventions await us in the future as we continue to explore and harness the power of atomic orbitals.
It's mind-boggling to think about, isn't it?
Yeah.
The possibilities are truly endless. Thanks for joining us on this deep dive. We'll see you next time.